Let's try to solve this problem. This is problem 63. The problem says that a chain of length L and mass M lies on the surface of a smooth sphere. In the last 2-3 exercises we have done, a ball is lying on a sphere. But now it's a chain. We shall see what difference does it make. Otherwise, the problem is same problem. The sphere has a radius r, which is much more than L. The sphere has a radius r. And a sphere is, r is much more than L. It means that the chain is very small with respect to the size of the sphere. Okay, that means, and the chain is tied on the top of the sphere. So let's say center is O, and let's say this point is A, and here there is a chain. That what difference does it make? Earlier it was a ball, now it's a chain. What difference does it make? When it was a ball, the mass was considered to be at one point. Now it's a chain which has a definite length. So mass is distributed. That is the only difference. Otherwise, the earlier problem and this problem will be same. First question is, find the gravitational potential energy of the chain with reference to the level of the center of the sphere. The first question is not a very difficult question. Only this is the reference level. First question is not a difficult question. Only the mass is not a center mass. Mass is now distributed. So we have to obviously take records of differential calculus. For that, let us say a small part of the chain. Let us say a small part of the chain dl, which makes an angle theta with the vertical, and this angle is d theta. In fact, in our drawing, d theta and theta has become almost same. In fact, d theta should be infinitely small with respect to theta. But assume that it is infinitely small with respect to theta. And this is the length of the chain which we are considering. This is the length of the chain under consideration. Now, here we find that mass per unit length, mass of chain per unit length, is equal to pi L. Right? And what is this length? This length is, of course, from your knowledge of geometry, this length is r d, where theta is always expressed in radian. This length is r d theta. And let us say a small part of the chain, of mass dl. That means the mass of this small length r d theta is considered to be dl. So mass per unit length is m by L. So this dm will be equal to m by L into R, because uh, length of this small part of the chain is r d theta, and mass per unit length is m by L, so it is r by L, m by L d theta. Now, what is the potential? Let us find out what is the potential energy of this differentially small part. If we write this is du, right, this is du, potential energy of this small part is equal to, will be its mass dm multiplied by g multiplied by, what is the height of this is, height of this is r cos theta. Height of this is r cos theta. So dm g r cos theta. R cos theta. Now we put the value of dm. dm is m by L r d theta. So it is m r by L d theta multiplied by g r cos theta. This is equal to mg r square by L. This is equal to mg r square by L cos theta. So potential energy of this small part of the chain is mg r square by L cos theta d theta. Now, obviously, we can find out the potential energy of the entire chain if we integrate this function from theta to L by R. This angle, the total angle will be, of course, L by R. I think if I try to write it, this will become very clumsy. The total angle is L by R. This total angle is L by R. Because L is the length of the chain, R is the radius of the sun. Total angle is L. So, potential energy when the chain begins at A is equal to of this m g r square by L, mg r square by L, its integration from 0 to L by R. Total angle is L by R into cos theta d theta. Cos theta d theta. This is equal to mg r square by L. Integration of cos theta is sin theta. So it is sin theta, and the limit is from 0 to L by R. This is mg r square by L. So now it will be mg r square by L. It will be sin L by R. Sin L by L upon R. The minus part will be sin 0 is 0. So we have not written it. So this is the first answer. What is the potential energy of the chain when it is at the top? Remember that had it been a small mass m, then its potential energy would have been simply mgr. Now its potential energy is like this. Okay? Second part of the question, suppose the chain is released and slides down the sphere. Find the kinetic energy of the chain when it has slid through an angle theta. Now this first picture has become so clumsy. So now we draw a second picture. Let us say the chain is here. Let us say the chain is here. Right? And it has said chain has already slid down the sphere. Find the kinetic energy when it has slid through an angle theta. That means it has slid through an angle theta. And in that case, this angle is L by R. This angle is L upon R in radian. This point is A. Let us consider this point is P. Right? Now, question is, find the kinetic energy of the chain. What we can do, we have found the potential energy of the chain when it was at A. In the same method, we can find the potential energy of the chain when it is at P. Then this loss of potential energy will be manifested as the gain in kinetic energy. So that is the method. So let us find out the potential energy at P. Right? So to find out potential energy at P, mention it, potential energy at P. What is the potential energy at P? Found, we have seen that initial equation that dE, we shall use this equation. We shall use, let me mark it here. Here we have the value of dE, which has been integrated. Now we shall integrate the same du, not dE, it's same du, that means differential potential energy, with a limit of theta to theta plus L by. So this potential energy will be equal to same equation mg r square by L, mg r square by L, and cos theta d theta, theta d theta. How we shall integrate it from the limit of theta to theta plus L by R. Theta plus L by R. Look, we are doing the same integration, but only with a different limit. This is equal to mg r square by L, mg r square by L, and differential of cos theta is equal to sin theta. Sin theta limit is theta to theta plus L by R. Right? This is equal to same. Now we put the limits. We put the limits. It is mg r square by L. Then within bracket we write sine of theta plus L by R. Sine of theta plus L by R minus sine theta. Minus sine theta. So this is the potential energy at P, the potential energy. So what is the loss of potential energy? This potential energy minus this potential energy. So we can possibly write for you to remember later on that kinetic energy at P will be equal to potential energy at A minus potential energy at P. If you write this in the note, it will be easier to understand it later. So potential energy at A was this mg r square by L sine L by R minus this. So in these two functions, we have seen that mg r square by L is the common. Mg r square by L is common. And we have sine L by R, sine L by R minus sine theta L by R, sine theta plus L by R, and this minus sine theta will become plus sine theta equal to sine theta. So this is the second answer. What is the kinetic energy of the chain when it has slid through an angle theta? Now there is a third part. Find the tangential acceleration, what is dv d theta, of the chain when it starts sliding down. Right? Now, it starts sliding down. That means when the chain has just started sliding down from the top, what is its tangential acceleration? Now, let me make a little space in the board. What is the tangential acceleration? Okay. Now, find the acceleration. We know acceleration will be force divided by mass, right? So we write that acceleration, this is the third, we come to the third part. So I draw a division line here. So we're not mixed up. This was part A, this was part B, and this was part A. Now we are at part C. Here we write tangential acceleration or any acceleration is equal to force divided by mass. This I am writing down at the very beginning because we shall find out force and then divide it by mass to find the total acceleration. Right? Secondly is S equal to R theta. This is one thing. Second, few points we write down. S is equal to R theta. S is the displacement and theta is the displacement in angle unit radian. And S is the linear displacement over the sphere. S equal to R theta. From here we get, since we shall do differential, we get S is equal to R d theta. Look, we are converting everything prepared for a differential equation. ds equal to r d theta. And from here, we can write that ds d theta, ds d theta is equal to r. Or from here we can write d theta ds is equal to 1 upon r. We shall need these functions later. Now coming to the basic thing, what is the relation between force and change in potential energy? This you remember from your earlier chapter. Force is equal to negative of differential of potential energy with respect to displacement. Why negative sign? Remember, if there is a displacement along the direction of the force, I repeat, if the displacement is in the direction of the force, then work is done by the force. As a result, the potential energy of the body decreases, right? So if force is equal to du ds, I have to convert this into d theta ds is equal to minus du d theta minus du d theta into d theta ds, because this d theta and this d theta will get eventually cancelled. This is equal to this d theta ds we have already got is 1 by r. So this is equal to minus 1 by r minus 1 by r du minus 1 by r du ds, right? Now, what is the potential energy in terms of when the body is at an angle theta? Potential energy of the body when it is at an angle theta now look how I am proceeding. I need a little bit more space here, possibly. So I'll just lift the board up. Some space here for me. Yeah, now we have enough space. Now, here we have found potential energy at P. Potential energy at P. Look very carefully. This is the potential energy at P. That means potential energy when the chain is at an angle theta. Rather, the starting of the chain is at an angle theta. So we write it clearly so that later on when you see this note, it will be clear to you. Potential energy when the chain is at an angle theta is given by at an angle theta is given by the equation by this equation is given by this equation. At an angle theta is mg square by L within bracket sine theta sine of theta plus L by R minus sine theta. This was the potential energy when the body is at an angle theta. Now, the technique that we shall use shall find the force, because force or acceleration they wanted us to find out. We shall find the force or acceleration when the body is at an angle theta. And then, since they wanted us to find out the force when the change starts, in that result, we shall put theta equal to 0. And immediately our answer will be obtained. Right? So, potential energy is given here. And we have found the force is equal to minus 1 by r du ds. So, force at theta is equal to minus 1 by r and du d theta, du minus 1 by r du d theta. That means this function has to be differentiated with respect to theta. So what do we write? Minus 1 by r multiplied by mg r square by L, mg r square by L, and differentiate this with respect to theta. If we differentiate this with respect to theta, sine of theta plus L by r will become cos of theta plus L by r minus, again, sine theta will become cos theta, and whole thing will have a, this is the force. Now we have to find out the force. I write it down here. We have to find the force when theta was 0. So here we put the values of theta equal to 0. Therefore, force. So force is equal to, this becomes r, and this r square gets cancelled. This becomes minus mg r by L minus mg r upon L multiplied by, when theta was 0, I write here, that is cos theta is equal to 1. So in this equation, if you make theta equal to 0, this will be cos of L by r minus 1. Minus 1. This is equal to, there is a negative sign outside. So we write m g r divided by L multiplied by 1 minus cos L upon r. 1 minus cos L upon. Now, force is equal, now they wanted us to find out acceleration, tangential acceleration. Tangential acceleration is F by mass of the whole chain. So it will be mg r by L, if you divide it by mass m, so mm will get cancelled. So we have only rg by L, rg by L multiplied by 1 minus cos of L by r. So this is the answer of the third part. Okay. Now we shall go to the next problem.